he's been around, so the benefit of having such experience as a speaker is you can get to ask real tough questions and get real life advice. Someone that's been through the mill and has seen a couple of things go well and a couple of things go not so well. The topic itself, I've got software in my bones, so keeping software soft is a very relevant topic because so often it becomes fragile and just breaks. Gerard also wrote this book. It's in our bookstore. Very good book. I can suggest it, so he doesn't have to sell it. I'll sell it for him. It's a worthwhile read, and it's a workbook. So, Gerard, thank you very much for joining us, and enjoy the talk.
All right, thank you. And lest the sheer size of this thing intimidate you, it's very useful for holding open doors. And the good news is you only have to read about this much of it. The rest is all reference. So it's about 200 pages that you might actually want to read through linearly, and then the rest is stuff you can refer to when you need it. Apparently in Japan, there's a named process. I can't repeat the name because it's in Japanese, obviously, where they cut the book into thin slices so they can actually carry it in their little messenger bags and read it on the subway. But now you can download it in PDF and iPub and all the other formats, so you can not have to deal with the sheer mass of it. So the theme of this year's conference is elephants, and it's actually very salient for me because people ask me how long it took to write a book so big, and I tell them it took twice the gestation period of an elephant, which was about 3.5 years. So, as was mentioned in the introduction, I've been around for a little while. You can probably tell from the amount of gray hair I still have left. So my background started off as a software developer, building telephone switches and been through a number of different sort of phases of my career. You know, all this stuff is useful to learn over time. What I'm going to focus on today is talking about software and what is it about software? Well, what does software mean, and why is it called soft? And what do we do to keep it soft? So I looked it up in the dictionary, and I came up with a bunch of these definitions. Now, most of these definitions are of absolutely no use whatsoever, but I'll just highlight the important bits. The programs used to direct the operation of a computer. Okay, well that's very helpful, isn't it? Anything that isn't hardware. Okay, technically correct, but not terribly useful. Okay, well let's try breaking it down into the bits and see if we can get a more useful definition. Where? Ignore that bit. Here's the important part. Any intangible items as services or products of artistic or intellectual creativity that are saleable. Okay, that's where. Soft. Easily changed in shape, not hard or stiff. Now, is this at all useful? Is this helping us understand what software is so far? I don't know, maybe just a little bit, huh? Well, from your experience, what would you call software if you had to come up with a name for it right now?
Bug hive.
Bug hive. How about slowware, because it takes so long to produce? Or finicyware, because it's so hard to get right? Or brittleware, because it's so hard to change? Any other names come to mind? Why is it that the stuff that we call software is just so hard to create and maintain over time and evolve as our needs evolve? I guess if it was easy, they wouldn't pay us the big bucks to do it, right? So why do we care how soft software is? We're just going to make this software and then we're going to ship it and we're done with it, right? But in Agile, we are going through this cycle of thinking about what we need to build and building it and testing it and deploying it over and over and over again. So we're cutting down our cycle times and having more and more iterations. And so we're spending more and more of our time actually evolving the software that we've already created. And the harder it is to evolve the software, the less productivity we get, the less value we can deliver to our customers, whether that's an internal customer for an IT department or whether it's an end customer for a product development shop. So we have to think about how can we keep our software soft so that we can continue to evolve it. How many are familiar with this situation? We build software, we throw it over the wall, back come flying over the wall, bug reports. This is the traditional approach to software development. Test and fix is, I think, one of the names, or code and fix. I just like to call it ping pong or battleship. Here's the release. Missed. Now, there's lots of analogies between software and other forms of things, and there's a lot of good ideas to be taken from things like lean manufacturing, Toyota production system, etc. The one thing I want to really point out, though, here, and I'm going to be talking a lot about practices that we can employ to keep our software soft, but the world is fraught with stories where people have copied the practices without understanding the principles, and they've had results that, well, let's just say they were not able to reproduce the results of the originals. And a good example of this has been the car business, where they all trooped off to Japan and watched how Toyota did things and brought the ideas back and tried to re-implement the practices here in North America. And they just haven't had the same results. And they certainly didn't have them very quickly. So you need to go beyond the practices to understand the principles of why the practices work and get the culture in place and so on. A lot of the stuff that Joanna was talking in the last session of the keynote. So I'm going to throw this disclaimer in right at the front, and now I'm going to dive in and talk about practices. So, the whole discussion around whether or not Agile has crossed the chasm, certainly lots of people are talking about it. I think Scrum has done a lot to spread knowledge about Agile, and a lot of people say they're doing Scrum. Why is Scrum being so successful at the time? Would anyone here argue that Scrum is the most successful Agile methodology? Anyone disagree with that? Who here is doing Scrum? Just throw up hands. Who here is planning to do Scrum? Keep your hands up. I want to see those who are doing Scrum or planning to do Scrum. Okay, you can put your hands down. Who is doing or planning to do some other Agile methodology? 2, 3. So what are you planning on?
Well, again, not specific Agile methodology, but probably blending it with some of the traditional approaches.
Okay. Anyone else specific Agile methodologies or just in-house? You got your hand up?
Sorry?
Did you have your hand up?
Yes. Well, we do have stories, iterations, like all the ingredients.
But you're just not giving it a name. It's just Agile.
Yeah.
Okay. So you're cherry picking. Best of breed. Okay. So most people are doing something that at least looks like Scrum, even if they don't call it Scrum. So Scrum has some good attributes. One of the reasons it's been so successful is because it was the first to the certification game. And it got a lot of mindshare that way. And there's this hunger out there in companies that are adopting something new to get people certified. I don't know why it is, but it seems to be really important to them. And Ken and company jumped on that bandwagon and took advantage of it and got the name of Scrum out there. The other reason I think that Scrum has been very successful is that it it's not that hard to say you're doing it, because it doesn't impose any engineering practices. And there's a good reason why. The original version of Scrum actually had engineering practices, but they removed it when they sort of standardized and started publicizing it, because they didn't want to impose a specific set of engineering practices. They figured that there was enough good engineering practices out in the world that people should be able to use whatever good engineering practices they have. It's assuming you have some. Problem is, many places maybe don't have such good engineering practices. So now they're expected to improve their engineering practices. So why does Scrum often fail? One of the issues, of course, is incomplete adoption of Scrum, using some of the practices and not all, not understanding why the practices work, not getting the culture, not understanding the principles. Part of the issue is it's only about management, so it doesn't help you, doesn't force you to improve your actual engineering practices. And if you don't have sustainable engineering practices that will work in a highly iterative development environment, it's going to be hard to get there if you don't really understand the principles of Scrum. And personally, I think this is one of the big elephants in the room, enter the elephant, which is a lot of people are doing Agile, but what percentage of them are actually doing sustainable Agile, where they will be able to continuously deliver high value, and they're not going to just code themselves into a hole because they're just creating a mess because they're working on such short cycles. So, what is it about Scrum that's supposed to help us introduce good engineering practices? Well, the key is actually this thing at the bottom, this inspect and adapt. That's where we're supposed to be doing continuous improvement. And in theory, we're going to be doing continuous improvement on our engineering practices. But if you're in a situation where your engineering practices aren't so good, how do you evolve to good engineering practices? Well, we're supposed to make our problems visible. That's the inspect phase. And then we're supposed to make changes to our process, adapt them, and then see how things work and inspect the results and keep repeating this. But if you don't know what a good process looks like, a good software engineering process looks like, how do you know where to go? How do you know what changes to make? And you can get into all sorts of analysis paralysis situations of people proposing competing things. And it's hard. It's really hard to evolve. So one of the things to think about is, how can we get a good development process? So we could sit down and theoretically design a new process. The problem there is if you've never experienced a good process, you don't know what's possible, how do you know what to put into the process? And typically this would be done by methodologists or process police. And these people often don't have the experience with modern processes. The reason they're in that department is because they're not software developers. So it's kind of a chicken and egg problem. It requires a detailed understanding of how the different pieces of the process fit together, how the different practices fit together. And let's just say there's not a lot of good, successful examples of people or organizations doing this. So another option is to adopt and inspect. What I mean by this is to pick an existing process that's shown to work and adopt it and then evolve it as your starting point. And a good example of this is a very common set of engineering practices, which is to use the extreme programming practices inside of Scrum. So part of this involves bringing developers up to speed on a bunch of different technical practices. And something that's actually starting to develop, is a relatively new thing, is the idea of Agile developer skills. And in fact, there's now two sources of training and, in fact, certification available. There's the Certified Scrum Developer program, which Ron Jeffries and Chet Hendrickson have put together under the auspices of the Scrum Alliance. And they do 5 full days of developer training. And it's all hands-on, people doing software development, learning the practices. And that 5 days includes the introduction to the Scrum concepts. Another thing that's going on in parallel with this is the IC Agile, or International Consortium for Agile, which is a process-independent way of certifying Agile developers. It's not Scrum specific or DSDM specific, but it's focused on making sure that training that's being delivered to developers would give developers the kind of set of knowledge that a hiring manager would be able to say, yes, this person's been exposed to all the things I would expect from a professional Agile developer. At this point, it looks like, and this is still in development, I'm actually involved in helping specify this, it looks like it's going to be a minimum of 10 days of training. And part of the idea there is to allow people to take pieces of it in different courses and keep track of which parts they've covered, sort of like merit badges. So I've got the refactoring merit badge, and I've got the pair programming merit badge, and when you get all the merit badges, you get the professional developer certification. They're also working on certification for all the other roles on Agile projects, like product owners and testers and project managers and UX type of roles and so on. The reason I mention these is because this indicates that there is a growing recognition that management practices alone aren't enough. It's not enough to have good Scrum Masters or project managers, good product managers or product owners. We also need to actually have the people doing the real work have a set of skills. And so really then the question is, what is the set of skills that these people need in order to do a good job? So I actually covered all this already, so I'm not going to say that again. So let's look at an example of what we mean by this. What are the Scrum practices? And I've sort of taken an old diagram that Ron Jeffries produced probably close to 10 years ago now. That sort of shows the different practices and how they relate to each other. This is the sort of the main Scrum practices: the product backlog, the product owner who's populating the sprint planning process, and having short sprints, which have remarkably gotten half the length since the original Scrum definition. Things like the sprint review and inspect and adapt. And then superimposing on this, well, how does this look when we're doing things XP? I mean, user stories actually aren't a Scrum concept. They're an XP concept that Scrum seems to have borrowed. And Scrum calls it a product backlog item, and it could be something other than user story. But just sort of evolving things to line the terminology up a little bit. Then there's a bunch of additional practices, things like collective ownership, having a common coding standard, working at a sustainable pace, having a metaphor for how your system is structured, continuous integration. And then those are sort of like the team practices, the technical team practices, and at the very middle here are the core sort of programming practices that individuals do. Things like test first or test-driven development, refactoring, design, simple design, and pair programming. So that sort of provides an overview of all the practices and how they fit together, and sort of how they sort of different parts of the team are involved in them. So let's look at some of these practices in a little bit more detail and think about how these contribute to keeping the software soft. So one of the key things here is that we need to have small increments of functionality. And why is that? Well, the software needs to be, the increments need to be testable, so we know that they're done. We need to have a continuous flow of value. And when Joanna was talking about iterations, the first thing that came to my mind is iterations considered harmful, because this idea of having everything finish at the end of the iteration, and so everyone's rushing it like mad at the end to try and get their code in because it's really bad to have things cross iteration boundaries. Well, it creates this real stop-start rhythm to the flow of value, which is actually bad. I'd rather have value being delivered on the first day of the iteration, second day, third day, testers being able to start testing, or product owners being able to accept functionality every day of the iteration instead of having it all arrive on day n-1 and then struggling to do the testing at the end of the iteration. And having the definition of what done looks like, the acceptance test, the story test available in the form of executable examples, critical to really understanding what's needed. And this avoids a lot of the stuff we talked about earlier, things like the test and fix ping pong or playing Battleship. So these are important practices from a sort of managing and providing the requirements and communicating between the product owner side of things and the developer side of things. These contribute to making the software soft, but they don't make the software soft by themselves. So what I really want to focus on today is things like continuous integration, having the automated tests in place, the automated examples, the automated unit tests, the test-driven development process, refactoring, and so on. Now let's start with continuous integration, because this is another one of these practices. If I walk into any of your organizations and I ask you, do you have CI? Do you have continuous integration? Well, let's try this out. Who has continuous integration? Hands up. Okay, keep your hands up for a second. So let's check this out. Keep your hands up high. Don't be shy. So the people who don't have their hands up don't believe they have CI right now. The people who have their hands up believe they have CI. There's three important parts to CI. You need to have a build server that runs automatically. And you can put your hand down if you don't have this. So who's got a build server? Everyone who said they're doing CI is a build server. Who's got automated run tests that run every time a build is done on the build server? Okay, good. And whose people do frequent check-ins? Like at least once a day. If you don't do it at least once a day, put your hand down. Okay, so we lost a lot of hands there. So ask yourself, what's continuous about checking in, you know, once every few days? Or you can put your hands down now, thanks. I know your arms are getting sore there. I can see the hands starting to tremble. Right, so the funny thing is, it's another one of these situations where we have a term. The term encompasses these three parts, and yet, once the tools are available, everyone sets up a server and it's sitting there running in the corner, but we're only checking in our code at the end of the iteration. So that's not continuous integration. Yes, we have a CI server, but we're not doing the CI practice, right? And the real value of the practice is actually checking in frequently. So we have small change sets. We're discovering our interactions between the code being built by developers continuously and not in a mini big bang at the end of each iteration.
Number one, what's the difference between when a software developer builds and makes sure that the system works before they check it in, and then they check it in?
So, and what's the difference between those two?
Between that and something that actually rebuilds the system after it's checked in. So in other words, they build and make sure it works before it checks in versus check it in and then make sure it works.
So why is it important for both?
What's the difference between that in terms of, I'm trying to understand.
In terms of complying to my definition of CI?
Yeah, yeah.
Okay, so part of the problem is if I build it on my machine and I don't check it in, well, no one else has the code yet. And other people are making incompatible changes in their version of the code. So our code is diverging. So the whole idea of CI is instead of going like this and then back together again, bang, is to come back in frequently. Little small changes where each of those can be basically checked. You discover much earlier and you have much more time to react to the changes and the things you learn, which is, oh my God, this feature and that feature are incompatible, or there's an interaction between these two features, and we didn't think about the test cases. How should it work in this situation? So you only find that out after people have checked in. Now you could argue that if I keep doing a refresh or a get or whatever from the server and get the latest code into my version, I'm actually doing that integration in my space, and that's a good practice to do if you have large changes. But it's still only on your machine, and it's quite possible that it worked on my machine, but once you check it in, it doesn't work on the server because I forgot to check some stuff in or something like that. So the only real official build is the one on the CI server. Everything I do ahead of time is trying to do quality checks on my own stuff before I submit it. But until I see it running on the server and passing all the tests there, it's not part of the build. It's not team coded yet. It's only my own personal sandbox. Does that address your question? So we notice that this definition of CI requires that we have automated tests. And the reason we need automated tests is we want to keep the cost of regression testing down. And the reason that's important is we're going to be running the test before we do every check-in. And if we're going to be checking in frequently, we've got multiple team members each running all the regression tests at least once a day, if we go with the definition that CI requires to check in at least once a day. Right? So that's a lot of testing, and we can't afford to do that testing manually, which is why it has to be automated. We need functional tests to make sure the functionality that we provided is actually working, that we implemented. So this is the executable examples, as you know, functional tests, acceptance tests, whatever you want to call them, things that describe how the product should work. And we need unit tests to ensure that the details of the code are working, because you can't test the code deep inside the system properly through functional tests. Right? It's just like testing the part of a car. After you've installed in the car, it's a lot harder to test that the fuel pump actually works properly. You can tell that it's getting some fuel to the engine, but you can't tell that it's actually working properly after it's installed. So you actually want to test it before you put it in. So it's important that we have all these tests before we check the code in. Because if we don't have these tests, we're checking in code that has no tests onto the CI server. And the next person who needs to run the tests can't tell whether or not they did something that broke something because there's no tests. So writing your test after your code is kind of futile. You really need to write the tests at the same time as your code and check it in with your code, as opposed to writing the tests first and then writing the code first and then writing tests later. So this really implies that you need to be doing TDD. So how many people are doing TDD? Okay. There's one person who confidently put up their hands. Is that a confident put up, or is that a... I can't tell from the hand gestures there the level of confidence. So I'd say there's one person who's definitely confident, several people who are definitely waffling about whether to call what they're doing TDD, and a few maybes, and a lot of, no, I guess we're not doing it. Okay. So, if we've got continuous integration, we're really doing all three parts, and we have some automated tests, although maybe we're not doing TDD, where does this leave us from a software perspective? Well, we can add new code, okay. We can change existing code because we have regression tests that will tell us that we broke something. We'll find out quickly, hopefully, that we broke something. In theory, anyone can change anything safely because the tests will protect you. They'll tell you if you broke something. That's where the safety comes in. And, well, does it imply the software is soft? How quickly can we do this? Is there anything here that allows us to do the work quickly? So it says we can do it without hurting ourselves, but it doesn't say that we can actually get the work done quickly and efficiently. Okay, so what else do we need? Let's talk a little bit about software design. Where does the design come from? So one of the really important practices we've learned over the last, I guess it's about 12 years now that we've been doing stream programming. You realize it's been 12 years and it's still a niche practice. Maybe I understand now why Joanna says we're not across the Agile. TDD is still in the early, well, that part left of the chasm. TDD has not made it across the chasm. I think that's pretty safe to say. So refactoring is one of the really important things, to actually be able to change the design of the software without changing its functionality. Right? So this is how we go from a design that works but isn't very clean to a better design, a design that is more flexible, that allows us to add new functionality more easily. And as she mentioned, if you're going to take 3 months to do refactoring, that's not refactoring. You can call it re-architecture. I call it doing a Humpty Dumpty. Why do I call it a Humpty Dumpty? Because I've seen so many people say, we're going to do some refactoring. They blow their system up with this wonderful new design in mind. And then they spend the next 3, well, it actually turns out to be 6 or 9 months or forever putting it back together again. Right? All the king's horses and all the king's men couldn't get Humpty Dumpty back together again. It's a high-risk move. Most companies can't afford it. And I've seen several companies go out of business as a result of failed refactoring attempts. So it's really important for refactoring to be done in small steps. Of course, you need to know where you're refactoring to. So you have to have some idea of what good design looks like. So that's a bit of an issue. Many people don't know what good design looks like. And you need to know how to actually go and do this in a series of small steps. Anyone remember those puzzles that you used to have as a kid? You know, little word puzzles, a little matrix, you know, it starts with CAT, C-A-T, and at the bottom it's got D-O-G, and there's a couple of blank rows, and you're only allowed to change one letter at a time. And every word along the way has to be a valid word. That's what we mean by small steps, is you always have to have a working system. Every refactoring leaves you with a system that still works, still passes all the tests. And you do this as a series of small moves. And you have to figure out how to get there from here. And if you can't get there from here, you have to figure out where you can go to that you can get there from. Right? So it involves thinking out sometimes a whole sequence of steps. And it takes skill. Where do people get this skill? 2 days of Scrum Master training. No? Do you teach refactoring on the Scrum Master course? Okay. So there's this big debate, I guess you could call it, between refactoring. People really hate the word refactoring. Some people anyway, because it sounds like refactoring is rework, which is waste. So we should do pre-factoring, which is getting the design right the first time. So who here thinks they are smart enough to get the design right the first time? Okay, fine. Well, you guys are all very humble. Would have expected at least a few people to put up their hands seriously. So if we recognize that we can't get the design right the first time, then we know we're going to have to do some refactoring. Certainly when we're dealing with unanticipatable requirements, we're going to have to refactor to address them. But there's actually a lot of people who believe, and most of them have the title architect, who believe they can design a system that handles all the current and known and unknown future requirements and get the design right. And they usually design frameworks that are impossible to actually use to deliver anything. It's kind of scary.
We usually have the concept of an architecturally significant use cases, which are specific use cases that are well known upfront. It says that, okay, to support this, I need to plan an architecture.
Yeah, you can come up with a bunch of architecture significant use cases and use those to define your architecture. But what happens when you discover a new one and it changes your architecture? Who here anticipated this little thing called the World Wide Web? What did that do to your applications? Could you build into your COBOL applications 20 years ago support for the World Wide Web before you thought about it? I don't think so. There's always going to be things that change that you can't anticipate. So any architecture that we have at a point in time based on a known set of requirements may be fine for that known set of requirements, but as soon as something changes, the world changes, or your business changes, that architecture is less than ideal, and you need to be able to evolve that architecture. And the way we evolve it is to refactor. So some of the more contentious engineering practices, like refactoring is not that contentious. There are people who say you shouldn't refactor, you should prefactor and all that stuff, but actually most developers are now at least understanding the concept of refactoring.
Are you saying architecture and refactoring? I'm trying to sort of pair that in my mind. And I mean, there's one way to look at refactoring where it's more of a code cleanup, if you will. It's not is it really happening at an architectural level? If I find an architecturally significant changed requirement, that's in kind of, isn't that more than just refactoring? Refactoring is cleanup, right?
Refactoring, well, we certainly do refactoring to clean up code. And that's, for example, it's easier to evolve code, ugly code that works, into cleaner code that works than it is to just write perfect code the first time. Because we don't know what the code needs to look like. But it's not the only purpose for refactoring, right? We can refactor code to make it more flexible so that it's easier to add new functionality. That's not necessarily cleanup. The code could be perfectly clean for the current set of requirements, just be hard to modify to add new requirements. So there's a lot of different reasons that we can use for refactoring. And one of the reasons is to evolve the architecture. Maybe we need to take a big clump of code and pull it apart into two pieces so they can run in different places and communicate over, you know, a messaging interface or something. So now they can be distributed across the network or across multiple cores or whatever. That would be an architectural change, right? And you know, what is architecture versus design? Does anyone have a good definition of what's the difference in architecture and design?
Architecture is making sure stuff winds up in the right boxes and that there are not too many arrows. But it is.
Yeah, architecture is boxes and lines. The way I define architecture is the thing that's hard to change and design is the thing that's easier to change. So architecturally significant decisions are the decisions that have higher impact and are harder to change your mind about later. I mean, it's really hard to come up with a good, clear definition of architecture. It's like, what's the difference between legacy code and non-legacy code?
Legacy code is the code that's referred to as the code that works.
Legacy code is the code I didn't write.
Yeah. Now, in the other room, Mike Feathers is talking about stuff. His book, which is very good, Working Effectively with Legacy Code, his definition of legacy code is code that doesn't have any tests. And personally, I really like that definition because legacy code that doesn't have tests is hard to change. Code that's hard to change is legacy code, right? It's code, we're stuck with it. Works, we have to maintain it, and we hope we never have to change it, right?
But code with tests can also be hard to change. If you got this whole superstructure of tests, 50 of them fail, when you make that one change, you're going to work hard to make all the tests
So I'll get to
reasonable.
that. I'll get to some of the things around what can keep code from changing. But it's sort of a question of what's necessary versus what's sufficient, right? So having tests is necessary to make it easy to change code, but it's not sufficient by itself. There's other things that we need. But not having tests can definitely make it a lot harder to change code. At least from a safety perspective, how do you know that you haven't broken any of the code when you change it? The code might be really easy to go in and change. I just open up an editor and I'm done. And the one situation I want to make sure works, I can test it manually and make sure that it works. But how do I know I didn't break something else, right? That's the safety issue. How do I know I'm not going to get a call from a customer after I put this into production screaming at me because I broke something that's really important to them? So, another question.
Yeah, it's about a couple of slides before when you said that separating the Humpty Dumpty from refactoring.
Yeah.
I mean, at one point when you're doing refactoring, you're going to have broken code. Sometimes it might be in minutes that you have a broken code. So where do you define that if you have a broken code for a month, then you're doing too far, or broken code for a day?
Well, let's go back to continuous integration. How frequently do you need to integrate to be considered doing continuous integration?
Daily, at least?
At least daily.
Yeah.
So if you don't have working code at the end of the day and the structure of the code isn't better than it used to be, you're not doing refactoring, right? You're either not improving the design, you're not evolving it towards your goal, the re-architecture goal, you're not taking small steps towards it. Or if you know, working on your own machine, no, I'm not ready to check it in yet. Well, how long has it been? It's been an hour, no problem. A day, you know, I'm starting to get a little bit nervous. After you've been off stream for a week and you haven't checked in, right, that's starting to be a problem. I can't deliver new features on that code base because it doesn't work. That's not refactoring. That's a Humpty Dumpty. All right, so as I said, some of those other practices are a little bit easier to swallow. They're things individual developers can do by themselves, off in a corner, without anyone sort of looking over them saying, no, don't do that. We'll actually have seen situations where people were told, don't write tests. You don't have time. And so what happened? The people who are used to doing TDD actually wrote their code with tests. And the people who didn't have the experience, they wrote their code without tests. When they put their code together again, different components being integrated, guess where all the bugs were? If you've done TDD, you know where all the bugs were, because they were in the other guy's code, because your code actually worked. And you got the code written just as fast.
But doesn't that come back to architecture? If it's architected right, then you get your coupling and cohesion issues right as a desired future state, and that'll significantly decrease the possibility for bugs, wouldn't it?
Who here can figure out what the coupling and cohesion on their code is? Okay, I see 3 hands. Okay?
Yeah.
So that means that out of, I don't know, 50 people here, 6% are capable of thinking about coupling and cohesion in the abstract. Right? You know how the best way to tell whether or not you have the right coupling and cohesion? Look at your tests. Your tests will tell you. If you can't write a unit test for a piece of code because you need all these other bits of code, your coupling's too high.
True.
Right? It's actually a lot easier to write code with low coupling and high cohesion when you're doing it driven by unit test. Anyway, I'm stealing my own thunder here. I'm going to have to stop listening to your questions because you're dragging me off schedule here. I'm just giving you a hard time. All right, so let's talk about some of the more contentious practices like test-driven and pair programming. You know, I managed to push out the wrong button here somewhere. Okay, so what are our goals of running automated developer tests? Well, one of them is to make sure that the tests are really quick to run. We shouldn't have to do anything every time we run the tests. They should be fully automated. We shouldn't have to have any manual steps. They need to be repeatable so we can run them over and over and over again. They need to be robust, meaning they need to provide the same results today, tomorrow, next week, next month. Doesn't matter how many days in the month or what time of day they're run or whatever, the test should continue to run properly. After the code has been written, these tests should act as documentation of what the code does. They should act as a safety net. When we run our tests, they tell us whether or not the code is working. If we introduce a bug, they will tell us right away. That will keep us from checking in the code, and in that way, they actually act as bug repellent. Wouldn't it be nice to just have some off you could spray on your code so no bugs would go into it? And if you have the right set of tests, when you do introduce a bug, you know exactly where the bug is because the test kind of says, the bug's right here. It's in these 5 lines of code. You don't have to go spelunking through the code with a debugger, single-stepping, and all that kind of stuff to find your bugs. So that's after the code's already written and you've somehow managed to introduce a bug. Before you've even written the code, the test should act as a specification to tell you how the code should behave. And this is what keeps us from putting the bugs in the first place. If we don't write our tests first, then we lose these 2 key benefits of having the tests. which is helping guide the development and reducing the amount of debugging that we need to do. Why is that? Well, so here's sort of a classic software development approach, all the steps that we go through. Focus on the middle line here. We've designed our software. Now we're writing some code. We're putting some bugs into the code. Well, we are. What's your personal defect insertion rate? If you write 100 lines of code, how many mistakes do you make per 100 lines?
105.
How many backspaces per minute can you type? Right? We put in tons of bugs. Some of them the compiler finds, underlines things saying that's not a valid variable, etc. Some take a little bit longer to find. So we're inserting defects, and then we get around to unit testing our code after we've written it. And if we've written several hundred lines of code, it might take us a while to get through that code and do all the debugging. And, well, debugging. What is debugging? It's the act of hunting down, finding that the code isn't doing what it's doing, figuring out why it's not doing what you think it's supposed to be doing, and then changing the code, redesigning it so it actually does what you're doing. So that all that brings us right back to here again, and we get to go do it again. So how does this change when we do TDD? So this is an example of rework at a very fine level here. What we want to do is take our unit test and move it before we write the code. And then when we actually write the code, we just run the test. And we instantly find out whether or not the code actually does what we said it's going to do. Okay? And when we do that, we find we don't have to do this debugging. It just magically goes away. It's really quite incredible. If you've never done TDD well, you won't have experienced the idea of debugging-less coding. How much time? Who here actually writes code on a regular basis? Okay. Who here writes code and spends less than 20% of their time debugging? Only 2 hands. Less than 50% of their time debugging? Who spends more than 50% of their time debugging? There's at least one honest person in the room. I teach developers about unit testing, and I usually ask this question at some one point. We're talking about things and talking about whether to do the test first and last, so I go through and sort of do a more detailed version of that poll. And it's interesting, it seems to be about split 50-50. Half the developers say they spend more than half their time debugging. And the other half come in somewhere between 25 and 50%. Just think about how much time we're wasting if we're spending somewhere near half of our time debugging.
Well, not everybody could be unit test, I'm sorry to say, but that's what it is.
Yeah. So that's what TDD is about. It's about helping us avoid putting bugs in. Do you have a question?
Would you consider writing unit tests a form of debugging? I find if I do have a bug, I write a unit test for it.
Well, yes, there's test-driven bug fixing, right? Which is basically when you know you have a bug, because you've been told about it, first thing you should do is write a test that fails, and then fix the bug and make sure the test now passes. And that's a way of making sure the bug never comes back. It's like chasing it out of your code and putting up a fence so the bug can't get back in. So this is what we mean by TDD and how TDD is a way of preventing defects. So now the problem with TDD is, in practice, I find that we tend to write at least as much test code as production code.
Sometimes more.
Sometimes more. In fact, it's anywhere, the range seems to be 100%, like basically double, right? As much test code as production code to twice as much test code as production code. If you've got more than twice as much, I'm going to start getting suspicious about the quality of your test code. If you've got less than as much, then I'm going to be suspicious about your test coverage. But if you're in that range of between an equal amount to twice as much test code as production code, you're somewhere in the right range. And the question is, isn't that going to double the cost of writing our code if we're actually writing twice as much code? And the answer is, in fact, it doesn't, because it saves you all this time debugging. There's that incredible amount of time spent debugging that you can avoid. So, for those of you who haven't done TDD, what does TDD look like?
The green bar.
Yeah, the red-green cycle. So here's what we do. We write a test. We run it. We watch it fail. That's the red bar. Then we write some code, just enough code to make it pass. That gives us the green bar. And we write another test, or write some more code in the existing test, run it, we watch it fail. So we just keep going back from red bar to green bar. And we just keep doing that over and over again. And if we're doing refactoring, we always do our refactoring on a green bar. Now, it's really fascinating to watch people doing TDD. I've seen people do TDD cycles anywhere from, sorry, am I at the camera? Wandering too far. Some people will take 20 minutes, half an hour per red-green cycle. I've watched people who take 10 seconds per red-green cycle. Imagine that, 10 seconds? Red bar. Within 10 seconds you got a green bar. 10 seconds later you got a red bar. 10 seconds you got a green bar. It's amazing. So the rhythm of TDD is this back and forth. I call it something like double entry bookkeeping. Write a test, write a hard-coded method that passes just that test. Write a second test, evolve the method a little bit, introduce a variable. Write another test, introduce some conditional logic in the code. And so we're evolving from the simplest design that could possibly work to something just sophisticated enough to pass all the tests that you have. And picking the next test to help us modify the code just a little bit to add some functionality. You never want to add functionality that's not needed to pass the test. One of the most controversial things about this process is we start out with trivial implementations that we know we're going to have to change. And people say, oh, isn't that a waste? Shouldn't we just put the variable in the right way? We know we're going to need it. Well, let's look at an example of that. Okay, so I write a test. Okay, I'm going to create this flight. Now I'm going to write some code. My test passes. Okay, so now let's evolve the test to make it a little bit more stringent. Let's assert that when we call to get seats on this flight, it returns the number we passed in. What do I need to make that code pass? The test pass. I can write this, so the first thing I'll do is I'll return nil, because I need that to get the compiler to actually compile this code if I'm working in a statically typed language. That'll still fail. So then I change it to return 10. That's a stupid thing to do. You're hard-coding the answer. Yeah, but I don't need anything more. I've only got one test, and the test says the answer should be 10. So I hard-code the answer. So how do I make sure that this thing actually stores it in a variable? Does it really need to store it in a variable? Well, if it does, if I need to remember different, flights with different numbers of seats, then I write another test. And when I write this test, it's going to fail. So now I have to introduce the variable. This is a very small step. I'm adding one line and changing one line of code. How hard is it to get this wrong? Why would I need to do any debugging when I'm taking such small steps? The beauty about going and working at these micro little increments is I'm never more than about 20 seconds away from discovering whether or not the code I'm writing is doing what I think it should. So now I'm going to write another test here. This test says, get seats should only return a value when the flight's in a certain state. If it's not in scheduled state, it should throw an exception instead. Okay, so now that test fails. So now I have to put some conditional logic into my code here. The other tests verify that it still works in the other cases, and this test has now caused me to change the flight to start having state. So I'm slowly introducing functionality in very small steps. And and I'm never far away from working code. I'm only a few seconds away. This allows me to slowly evolve the code into supporting all sorts of functionality, and I'm never at a point where I've built up an inventory of defects where I don't know how many are in the code, and I don't know how long it's going to take me to actually remove all these defects. The so-called debugging period, right? So the nice thing about this is that there's a small overhead to writing the additional tests, and the overhead is proportional to the amount of functionality I'm adding. And it's very easy to predict how long it's going to take me to finish things, because I don't have this morass of, well, I've only got 2 bugs left to debug, and how long is it going to take? Well, it could take half an hour, or it could take all night. Okay, so we've gone through, we're going to do TDD, because my wonderful presentation has convinced you that TDD is the right answer. So now you can all start doing TDD. How are we doing against this goal of keeping software soft? And you can tape on the floor to tell me how far I can wander.
I'll follow you, don't worry.
So we've got continuous integration, all 3 parts of it, checking in frequently as well. We've got our automated tests. We're writing them first. We're doing TDD. We're evolving our code through refactoring. Do we have soft software? Who thinks our software will be nice and soft now, easy to change? Sorry, was that?
We still have a half an hour left. So
Still have half an hour. We can't be there yet. It's too early. An astute observation, although not based in any sound science. What else could possibly go wrong? So the answer is the software could still be hard to change. Why? Did you have a thought there? I see a hand starting to go up.
Poorly written tests.
Poorly written tests. The tests are helping us detect when we have bugs in our code, when we introduce new bugs in our code. But the tests are actually acting as almost like a fixative. They're holding the software into shape. So what happens when I change the functionality?
All the tests break.
Well, that's the question, is how many tests break? If one test breaks, it's going to be relatively easy to figure out. Now, if I change the code and no tests break, what does that tell me?
Concerning a little bit.
Sorry, say that again?
It might be a little bit concerning.
That might be a wee bit concerned, because how good are my tests? I just changed the code that they're purportedly proving behaves the same as it did before, and I just changed the code and it says they're behaving the same as they did before. So if no tests break, this is clearly wrong. But what happens if I've got hundreds of tests breaking? Ay, ay, ay. How long is it going to take me to fix hundreds of tests? I just changed one line of code. All these tests over here broke. Why are they all breaking? It's because they're written in a style that makes the tests sort of highly dependent on too much of the code. So this leads us to the topic of maintainability. So if we look at, ignore the part above the line here, this part down here, this is how much it's costing us to write software over time. And we introduce test automation, that's the effort above the line, our automated unit tests. So when we start out here, and we're just starting out TDD, we're going to find that there's a lot of extra effort involved because we're not good at it yet. We don't know how to do it. We're learning. We have to get over this hump of getting good at writing unit tests. And then, once we've done that, over time, we should find that our incremental effort to write tests, in addition to the production code, should be a small fixed amount. And that should be offset by the effort that we're saving, because why? Where are we saving all this effort?
Debug.
Sorry, what did you say?
Debugging?
We're not spending any time debugging. So, if we're writing our tests first, and the tests are good quality, helping us understand what we're supposed to be doing, we will save enough effort here to more than offset the extra cost of writing the test up here. If we are doing that. If we are writing our tests in a style that makes the test harder to write and harder to maintain, then the effort above the line goes up. If we're writing our tests too late, or writing tests that aren't good at pointing smoking gun style at the piece of code we just broke, we're going to spend a lot more time trying to figure out what went wrong. And so we're not going to have nearly as much effort saved here, and this ongoing effort is going to be more than what it would have been without having the automated tests in place. And at that point, we're in a precarious position because we've invested all this effort into doing TDD, and someone's going to say, hey, we can't afford to do this TDD. It's costing us more than before we did it. Yeah, maybe the quality has gone up, but we can't afford to delay things just so we can do TDD. So it's really desirable to be in a situation where this ongoing effort here is actually less with TDD than with tests after. So what does it take to do that? So if we look at our goals for our automated testing, as we said earlier, they should act as a specification for what we're going to write. They should act as documentation after we've written them, and so on. We want to be able to run the test easily and quickly and get repeatable results. So if we've done our test first, that will give us the benefits of getting the debugging, avoiding the debugging and saving all that effort back. But how can we avoid having a lot of maintenance cost on the tests? So here's an example of a test. And don't even try and read that. The point of this test is, this is the kind of test code that developers often write when they're not very good at unit testing. It's a skill like everything else. Some people write really nice, clean production code. Some people write really messy and hard to understand production code. What are the odds that those people are going to write nice, clean test code? Yeah, not that good, huh? This is what that test should look like. Okay? So, how can we get from the code on the left to the code on the right? Well, let's take a look. What this is actually doing here is we're just doing some testing of an invoice. Invoice has an address and a customer, and you have to have those before you can create an invoice. And what we're really trying to do here is test that the line items calculate correctly. So let's take a look at this test here. And because it's a little bit too small a font to read the whole test, let's focus in on one part of the test here. This is the part where we're actually looking at the outcome. We're looking at the resulting line items, and we've got a bunch of code here. So what can we do to make this code clearer? Is it easy to tell what the intent of this test is, reading this code? Technically correct, but hard to understand. It actually does verify what it's supposed to verify. But who's this test written for? It's not the reader. It's written for the compiler. So, what's an obvious thing on here that we could change?
The if statement up top.
The if statement. How about something even simpler? What does the last statement do? Assert true, false.
Oh. Yeah, that's just fair.
What does assert true, false do?
It always fails.
It always fails. So why don't we just write that clearly instead of being an obtuse assertion? So, if you get there, you should fail this test. Okay, so at least now we understand what it's doing. Now, we can look at some other things on here. I'll get to the if statement in a minute. We've got a bunch of hard-coded data in here. What does this data mean? What's it saying? How is this acting as a specification for what the software should do? Just a bunch of hard-coded constants. Don't know what that is. Now, hard-coded things can cause tests to be fragile, meaning they may break later on when you change something. So what you want to do here is, instead of comparing a bunch of hard-coded constants actually do calculations so you can see what should happen and compare whole objects instead of individual fields. Now doing it like this, comparing one object with another object, field by field, is messy. And we're going to do this over and over again in many different tests. So we don't want our tests to be verbose like this. We want to describe the intent of what these lines are doing. So we can extract that out into a custom assertion, which basically says, make sure these two line items match. The expected item, which says this is what it should look like in the actual item that the invoice returned. So now we have a much simpler piece of logic here. We still have this if statement. What's wrong with if statements in tests?
You should have logic in your test.
Yeah, we don't know, it's not actually stating what should happen. We have logic that we have to reverse engineer. And how do we know which path of the test we're going down? As a general rule, any conditional logic in a test is a bad sign. So it's much simpler just to never have it. And it's very easy to remove this. What is this if statement actually doing?
Verifying.
It's saying, well, don't bother doing the assertion if there isn't one line item, because there might not be any line item. How could we do that simpler?
Move it up top and just assert on the field.
Sorry, say again? We could throw an exception. How would we throw an exception?
You assert on it.
By doing an assertion.
Yeah.
So we should state what should be the outcome rather than putting conditional logic to verify the same thing. So simply by replacing this with a simple assertion, a guard assertion, assert equals that there's one item. If there isn't, the test will fail. If there is, now we can start looking at the details of the line item. So it's a lot easier to understand what's going on. So we've greatly simplified here what this test is saying. So let's go back to the whole test now and look at some other sources of ugliness and hard to understand. So down here is our updated code. Now let's look at these. What happened there? I'm going the wrong direction. That's the problem. So let's look at this last part of the test here. There's a finally statement in my test and a bunch of deletes going on here. What is this doing to help us understand the behavior of the system under test, the code that we are trying to describe the behavior of?
That it has permanent side effects.
Okay.
That you need to clean up after.
This cleanup here is basically just housekeeping. It's not specifying how the system should behave, how the code we're testing invoice should behave. It's just overhead. It's housekeeping. Why do we have this here? Let's look at it. Anyone see anything wrong with this code other than the fact that we even have it? Is this code reliable? Why is it in a finally?
Because it might die or crash.
Well, because assertions cause the test to fail. How do they cause the test to fail? They stop execution in the middle of the test. To guarantee that these deletes happen, we have to have a finally. But does this guarantee that all the deletes will happen?
No,
Why not?
because one of the deletes might fail itself.
If one of the deletes fails, the rest of the deletes won't happen. So we think we're being good citizen here and cleaning up after ourselves, but we're only cleaning up after ourselves sometimes. So we could end up with these objects floating around in space, getting in the way of future test runs. It's like basically a test object leak. It's like a memory leak, but with a lot of the same characteristics. We don't know where it leaked, but it's causing grief for us now. So to actually make this work properly, we'd have to do that. Okay. This is clearly not a scalable solution. Okay? So what can we do instead? Well, one thing is we can move this stuff into the teardown method on a test. But does this solve the problem? No, we'd really need to do that. All this does is move the problem. And it got it out of every test, and now we only have it once per group of tests. But it's not a good solution. So what else could we do here? Well, first thing is we really don't want to deal with persistent objects in our tests. Because a better architecture would allow us to just create these objects in memory and not have to worry about them persisting past the lifetime of the test. But even if we have to do that, we should have a more scalable solution to this. And one of the ways you can do this is whenever you create objects that are persistent, remember you've created them in a generic way. Simple method like add test object to a collection. And then in your teardown, you call a utility that tears them all down. And hey, that utility method can be tested. So now you know that it actually works. And then that piece of code looks something like this. And it's guaranteed to work because it actually goes through and continues on even after one of them has failed. So by doing something like that, you can get rid of all the teardown when you need to have it. Although, like I say, really most unit tests shouldn't have to do any teardown because it should all be working within memory objects, and garbage collection should do all your teardown. So there we've cleaned up the middle and the back end of the test. Now let's look at this front part here. How good a job is that doing helping us understand what the code's supposed to do? Why are all these statements here?
Create users objects.
Well, let's see, if I tried writing this statement here, the first thing the compiler is going to tell me is, oh, you need a customer, because invoice constructor takes a customer as an argument. So that causes me to go back and create a customer. If I can't create the customer without having these addresses, because I need these two different addresses, so I'm kind of getting sucked down this hole by the constructor signatures. So assuming I did get sucked down that hole, now I've got this ugly code. How can I clean it up? Well, one of the things I want to do is look at it and say, which of these things don't matter? If it's not important for it to help us understand what the production code is supposed to do, it's important for it not to be in the test. So when a person reads a test, only the important stuff should be in the test. If it's not important, it shouldn't be there. So how can I get rid of this? Well, one of the things I can do, oh, sorry, this is not showing up well in this projector. This is saying hard-coded test data, obscure test, and that can also lead to unrepeatable tests. So let's try and get rid of some of this data that's irrelevant. One of the ways you can do that is just to use little utility methods to create the things of the appropriate type, in this case strings, that are unique to this test so that you don't actually have to worry about them running into each other if you're saving them in databases or whatever. But that kind of makes this thing ugly. And you really want to read that? If it's not important to be there, why can't we just get rid of them entirely? So why don't we go through and remove these things? So what we can do is say anything that's not relevant here, let's just get rid of it. And so what we're going to do is going to call a factory method that creates us an object ready to use. And we'll only pass in the things that we care about. And in this case, we don't care about anything, so we don't pass in anything. And those factory methods will create the object, fill in all the necessary fields. And it turns out this is really useful when I evolve the system and have to add a constructor argument. I don't have to go back and revisit all my tests. I only have to revisit the utility methods. Now, this code is still a little bit hard to understand. But the font size is coming up a bit. We can start to read it, even at a distance here. What else is wrong here? Let's look at these lines. How are these lines helping us understand what the code is supposed to do? Are they relevant? No. Can we get rid of them? Of course. So let's get rid of these. Does that look better? Is it good enough? Is the customer important here? Evidently not, because we're not passing any arguments to it.
Why not create a mock object for the customer?
We could create a mock object, but it's still more work. In this case, I just want to get rid of it entirely. What I really want to do here is say I need an invoice, because that's the thing I'm invoking methods on, but the customer is irrelevant. So let's just create an invoice. So by using the factory method, I can get rid of that. So I'm just constantly asking myself, what's important, what's not important. If it's not important, get rid of it. Just repeat over and over again until you distill this thing down to the bare essence of what it's trying to say. So at this point now, I have 2 lines of code to construct the objects I need. One of them is the argument to the method I'm testing. And the other, sorry, this one here, and the other is the object I'm invoking the method on. I can't get rid of those because that's part of the definition of what the code is supposed to do. So I've boiled this down to the bare essence of what I need there. Now that we've got that, let's go back down here and look at this. What is this code actually doing? We've already simplified it considerably from what it did before, but what is it actually saying from a specification perspective? And I'll give you a hint here. This box here, which you can't read, says mechanics hides intent. You have to read the code to reverse engineer what the intent is. What's it saying? It's saying, let's make sure that there's one line item, and now we go and get that line item from position 0. Whoever came up with this crazy concept of using 0 as the location of the first item. And then we're actually comparing the two line items, the expected and the actual. Someone describe to me what that's saying in plain English. You have to put a comment on that group of lines. What would the comment say? Something like, there should only be one line item and it should look like this. Right? Do I need 3 lines of code to say that with some complicated Java or C# or whatever in there? Why can't I say it that simply? Why can't I just say something like this? Assert exactly one line item. Expected, actual. Or, in this case, what we're saying here is, make sure this invoice only contains this one line item. So we've taken the mechanism that we're using to extract the line item and find it and count them, etc., and we're hiding that behind the utility method. So now we've got a test here. We're down to 5 lines of code. Most of our tests should be this small. Okay? So now let's take a look at the class that has all these tests on it. And if you've done any tests in FIT and used or other forms of keyword testing, you're going to find that this test is looking an awful lot like the kinds of tests we'll write in our acceptance test-driven frameworks. Do you have a question?
Yeah, I'm just saying that when you say simplify the test, I'll be very short.
Yeah.
Are we just saying that, well, simplify, I mean, rather than putting all the piece of code within the test, just make like combine them in functions and make them easy to read. The functions are easy to read, but the actual line of code still remains the same. I mean, aren't we like
You lost me in there somewhere.
Aren't we like abstracting the lines of code into a function name like this, but the actual lines are hidden from
the lines are hidden, yes. I'm hiding non-essential details while keeping the essential details in the test. What I'm really doing here is creating a language for describing this behavior. And what do I mean by creating a language? I don't want to write my test in Java or C# or Ruby or C++. I want to write my tests in business language. That's the big difference between this test and the test we started off with. We've pushed most of the computer sciencey stuff out of the test into the utility methods, and we've left things that read much more like plain natural language. Okay, now let's look at another test here. So to see how we can use this domain-specific language to describe other scenarios. So here is a test case class that has a bunch of methods, test methods on it, that describe the behavior of add items and remove items off of an invoice. And we've implemented one item. Now let's look at what happens if we create an invoice with duplicate items, items with the same product. What should that behavior look like? Let's start with that same test as a starting point. So I just clone this test, change the name, and now I'm going to vault this test into the test for duplicate items. What do I have to add to that to specify what should happen here? Well, first of all, let's start with the expected outcome. Instead of having a single quantity, it should now have the quantity of the 2 adds. So we're going to call add twice, and we're going to call it with quantity 1 and quantity 2. We add those 2 together, and we're going to have one line item with the resulting sum of the 2 quantities. Well, that's not going to compile because we haven't defined some of these things yet. So let's add our other item. Oops, there's a typo there. That should be product. Well, actually, no, that's correct. That's the same product. And there's our other quantity. Now imagine having to write this test if we were writing it in the original style versus this domain-specific style. How long this test would be, how much code you would have cloned, and how much harder it would be to express what should happen here. And if I compare these two tests, look at them side by side, it's going to be very clear what's different. The other one had only one quantity on it, this one has two. This one is setting up the expected item with the sum of the quantities instead of just the one quantity. All right, so let's look at another test here. What happens if we're going to create a test with several items? Well, let's start off here again. What does the assertion look like? Instead of saying assert exactly one line item, we're going to say assert exactly two line items. Here's my invoice, here's the first line item, here's the second line item. Now, I'm calling a utility method that I haven't even written yet, because I'm expressing intent. Now, after I finish writing this test, I'll say, oh, I better implement that utility method. This won't compile. So I'm actually using a pull model, pulling this utility method into existence. I'm writing the test the way I would like to write it, as opposed to writing it using only the code that's already available to me. So I'm actually helping define the language. Once I've defined the pattern of what I want these assertions to look like, I can add additional methods with different versions of the name and signatures. So there's my second item that I need to have here passed. And I'm going to call add item with the second item with the quantity, and I need to create the second product. So all I'm doing here is using the same statements I did before with slight variations, because I've already defined the language I'm using to speak about the requirements. So that's an important concept, is to make your test easy to understand, because you're going to spend a lot more time reading tests than writing tests. Now, if you do it the way I've shown you in the second example of actually writing the test this way, writing the test is also easier and faster and much less likely to have bugs in it. But even if you're always refactoring to make your tests clean, like we did starting with the first test, the effort you put in to refactor and clean them up will be repaid every time you read that test. And every time you run tests and have tests fail, you're going to go back and read tests. You're going to be reading tests tens or hundreds of times for every time you write them. So it's really worth spending a little bit of time to actually clean up the tests. And that makes a big difference in terms of what your maintenance cost is on your tests. So that's an important factor in keeping the software soft. Now, the last thing I want to talk about is pairing. So pairing is probably even more contentious than TDD in terms of how many people are doing it. Who's pairing? Oh, actually, slightly more people than said they were doing TDD. And I would say the hands looked a little bit more definitive about the answer. There was a lot less, yeah, should I, well. So I'm really encouraged to see that well, maybe almost 10% of the people in the room were doing TDD, or pairing, sorry. That's good. So when we talk about pairing, there's things like, a developer and a tester pairing, helping each other write tests. You probably assumed I meant just two developers pairing, didn't you? So how many people are pairing? Did the number change at all? Who's doing cross-functional pairing? No, only one. And a maybe, 1.5. And the rest are all developer pairing. Okay. There's lots of opportunities for cross-functional pairing, improving the quality of what we're doing. Analysts and developers pairing, working on requirements. Two project managers working together to define their interdependencies. Isn't this a waste, having two people doing one person's job? I flew here. I looked in the cockpit. We're cruising along at 20,000 feet. There was only one pilot. Well, if you don't count the little kid in the baby seat. Would you be nervous if you were in a commercial jet with only one pilot? Why aren't you nervous? Your life depends on code that was written by only one person working by themselves.
Well, it has a negative side of not pairing too.
What's that?
Well, as much as they have positive things, some of the things, it depends of the level of developers, if they're on the same level or it's more beneficial. If one is more advanced than the other, well, it's definitely beneficial for the other one to gain experience. On another side, the experienced developer is holding most of the heavy load.
It's true that when one developer is better, faster, whatever you want to call it, more experienced than the other developer, they feel like they're being held back. But it's an investment, because the other developer will be rapidly learning. It's a form of cross-training. In fact, every time I pair with someone, I learn something, and it doesn't matter who I'm pairing with. If I sat down and paired with any of you, I bet you I would learn something. So the learning that goes on in pairing is actually a completely misunderstood and underestimated value. It's not just about how much code you're producing, but focusing just on the production of the output. It's all sorts of examples of places where you really want to have two people, because keeping the whole problem in the head, doing all the things that, that they're required, is just too hard. Here's a little example here. Why isn't that one going to go? Oh, I'm pushing the wrong button here. Full screen. Okay, come on. Hopefully the internet connection is working here. All right. Let's try that again. You think these guys could go as fast with only one guy in the car? Can you hear what the co-driver is saying? He's calling out what's coming up around how big the next corner is, how tight it is, how fast you can go.
Let's read that without getting sick.
Let's stop that. That's enough for now. But that's just an example of a situation where having two people sitting together, they're not doing the same job. One isn't sort of just along for the ride. They're actively contributing. And proper pairing is the same. When you have two people sitting there working together, they're thinking about different things. If one person is typing away, they're thinking about syntax. The other person is thinking about design, or what tests we should be writing next, or what would be the alternative to this idea. There's a very complementary behavior going on between people who are pairing effectively. So it's something that it does take a little bit of time to learn. It's something that there's certain sort of hygiene factors, like some people don't like working with anyone else. Some people don't shower regularly, and it's really sad that we work in an industry where you actually have to mention this to people sometimes. And, really, it would be good if you showered once in a while.
As long as they don't want to pair.
But it's actually very effective, and especially when you're learning how to do some of these new practices, it's a lot more effective when you're pairing. So lots of examples of situations in which it takes two people to do a good job. And I would argue that software development is actually one of them. All right, so we're talking about a lot of different practices. And one of the important things to understand is how all these practices relate to each other. So for example, here we've got frequent delivery requires that we have good quality. If we don't build quality in, we're going to be spending a lot of time doing test and fix cycles every time we try and deliver. It's important that we have small stories, because that allows us to deliver in smaller increments. It's important that we have continuous integration, because that's one of the ways we keep the quality level up. It's important that we do TDD, because that's how we get the tests in place and how we avoid putting bugs into the code in the first place. It's important that we have the automated tests to run in continuous integration. It's a lot easier to do TDD when you're doing simple design. And it's a lot easier to write automated tests for simple designs. And if you're doing simple design, you need to be good at refactoring because you need to evolve the design in small steps. So all these different practices are all sort of building on top of each other. And the problem with cherry-picking practices and say, oh, I'm going to do this one and I'm going to do this one, that one's not acceptable here for political reasons. All of a sudden, you take one of these things out, and all these interdependencies are all of a sudden, well, if you're not doing TDD and pairing, then where are you getting the quality? You know, you need to do something else to compensate for the fact that there's only one person writing the code. You should be doing code inspections. You should be doing other practices that provide the same benefits. You need to have ways of cross-training people on the code, teaching them skills, because now they're not learning it by sitting next to people. So there's a lot of benefits that are lost when you leave out important practices. So I just want to finish off here, and I'm actually just out of time here, is if we're going to do highly incremental development, which is really what we're talking about here when we're doing Agile, is we have to change how we actually build the code. It's not enough just to change how we manage the teams. We have to change how we actually construct the code so that we can deliver this continuous stream of value. And we have to reduce the cost of change, make the code easier to change, easier to add new functionality. We can do that by reducing the likelihood of introducing defects in the first place, right? So better quality in instead of trying to remove them after the fact. And make sure we can find the defects we do introduce very quickly through feedback mechanisms like having the automated tests and continuous integration that runs the tests regularly. We need to make our stories small so they fit inside single iterations. Doesn't mean that they have to finish in the same iteration that they start, but we need to make sure that we're delivering many stories in each iteration. We need to have all three parts of the continuous integration practice. We need to do TDD both at the acceptance test and the unit test level. We need to have automated tests being executed very frequently. We need close teamwork, and especially pairing, not just cross-functional pairing, but also interdisciplinary pairing. And we can get there either by inspecting and adapting, or we can adopt an existing set of practices like the XP practices and use those. So that's basically all I have to say here. If you have any questions, I'd be more than happy to answer them either now or over the lunch break. They're serving food out there already, so I don't want to actually hold you here any longer, but more than happy to answer questions.
I have one question, is about refactoring unit tests. When originally you're doing TDD, you write your test and your test failed, and that's how you make sure your test is actually functional. But when you refactor your test, how do you verify that the test that you refactored is still, you don't intentionally break your code and make sure your test now fails?
Sometimes.
You reverse the process?
Yeah, sometimes you do exactly that. If you want to test your test, you have to make sure that the production code actually has a bug in it. So go and change the code, watch the test fail, and then undo the change and watch the test pass again.